Good afternoon. Welcome to the session on emission control, ammonia SCR and deactivation. My name is Raul. I'm happy to co-share this session with Professor Justin Nossestein from Northwestern University. And it's with great pleasure that I'm here to introduce the keynote speaker for this afternoon. Is Professor Isabella, who's joining us from the Politecnico di Milano. She's going to talk about the mutual interaction of Soot Combustion and ammonia SCR in SDPF. With that, welcome. Great to have you here, and I'm looking forward to hear your talk.
Thank you very much, Mr. Chairman, and good afternoon, ladies and gentlemen. Let me, first of all, thank the organizers for having given me the opportunity to be here today with you and to share some of the recent results that we have been collected at Politecnico of Milano, analyzing the SDPF system that is used to simultaneously reduce NOx and PM emission from the exhaust of diesel engines. Actually, I'm going to spend a few words on the experimental study that we did, looking specifically at the mutual interaction between the ammonia SCR and the soot oxidation chemistry. I would like also to acknowledge the co-author of this work, Fabio Marchitti, who is the PhD student who actually did all the work, and Enrico Tronconi, who has been working always with on the SCR topic. So, first of all, I would like to spend a couple of words on the SDPF concept, which may be rather new for you. Actually, we are used to have on board of vehicles two different devices to control both NOx emission and PM emissions. And the most used ones are indeed, at least for heavy-duty application, the ammonia SCR and the diesel particulate filters. Well, in order to reduce the number of the after-treatment devices present on board of vehicles, to reduce volume, cost, and weight, and also to move closer to the engine, the SCR device, in order to improve the thermal behavior, but also to take advantage of the superior properties of NO2 with respect to oxygen, in order to improve the passive regeneration of DPF. It has been proposed to merge the two technology into a single one that actually is a workflow catalyzed filter in which the highly porous walls of the filter are impregnated with an SCR catalyst. And the system is known as SDPF or SCRF or WSCR system. And of course, we would like to have in this single system the same performances as typical of the two different devices, both in terms of NOx emissions and particulate control. And this takes me to the goal of this work, which was the analysis of the mutual interaction between the SCR and the soot oxidation functionalities in the single device. And specifically, we wanted to look at the competitive consumption for NO2, which is indeed one of the main reactors for the SCR process, and also we wanted to understand if and how the presence of soot may affect the DNOx performances. So, accordingly, this is the outline of my presentation. First of all, I would like to spend a couple of words showing you the data collected analyzing experimentally the intrinsic kinetic activity of the SCR and soot oxidation, but more specifically the interaction between these two functionalities. And we did that over a copper-zeolite catalyst and using the Quintex U as model soot. Then we wanted to investigate what happens if we use a real soot. And for that, we performed a number of experiments, always using the copper-zeolite catalyst in the presence of two different real soot, the LAT and the NTU soot, and I'll be back on that in a minute. Then we also wanted to understand how the catalyst may affect the interaction between the chemistry. And to do that, we performed a number of experiments using an iron zeolite catalyst in the presence of the NTU soot. And finally, I would like just to touch briefly upon a final work that we have been doing in collaboration with the Laboratory of Applied Thermodynamics in Thessaloniki and MTU in Friedrichshafen to implement the findings of the fundamental work into a model of the real SDPF component. So, a couple of words on the method that we use in Milan. We received the SDPF components from our industrial partners. We remove the plugs and then we crush and sieve them into fine powders in order to avoid mass transfer limitation, and we mix them with the soot powders according to loose contact methodology. Then we load the powders into a microreactor where, of course, we can control the feed gas in order to analyze both the SCR or the soot oxidation chemistry. The gas exit in the reactor are analyzed simultaneously by mass spec and UV and IR analyzers. As mentioned before, we tested two commercial catalysts, a copper-zeolite that was impregnated into a silicon carbide DPF system and an iron zeolite catalyst that was impregnated into a different substrate. And we also tested different soot, the Brindex-U, very well-known reference model soot, but also two real soot. The first one was provided by the Laboratory of Applied Thermodynamics in Thessaloniki and generated by using a Daimler passenger car engine, and the second one was provided by MTU, generated by using a large no-road vehicle. So let me try to start with the experimental results obtained using the copper-zeolite and using Brindex-U as model soot. And according to hierarchical order, we're going first to look at the effect of NOx on soot oxidation. We will start with the pure oxidation played by oxygen, and then we add and we will test different oxidizing mixture which are typical of the SCR chemistry. So we will test the effect of NO in the presence of oxygen of equivalent amounts of NO and NO2 and of only NO2 in the feed stream. Then we will address the effect of ammonia on soot oxidation, or better the effect of the simultaneous presence of ammonia and NOx. And to do that, we will analyze again the four different reactive mixtures, but in the presence of ammonia. And eventually, we will look also at the effect of soot on the ammonia SCR activity. And we're going to look at the main reaction system typical of the SCR process: ammonia absorption, ammonia oxidation, the standard, the fast, and the NO2 SCR reaction, where the experiments have been performed by having the soot loaded into our microreactor. So I will start with soot oxidation played by oxygen. In this case, we are feeding 5% of water and 8% of oxygen into our microreactor, and we ramp up the temperature from 150 up to 700 degrees C, having, of course, into the microreactor both the copper catalyst and the soot. We can see that we have soot combustion starting from 200 degrees C, small production of CO2, and then the presence of oxygen, of course, enables soot oxidation light off occurring at 450 degrees C, with production of CO2 and CO, according with these two reactions reported here, of course. The same experiments has been then performed by co-feeding 500 ppm of NO in the feeding mixture together with oxygen. And we can clearly see that the situation in terms of CO2 and CO production is very similar to what we have when we have only oxygen in the feed stream. Indeed, the light off is still occurring at 540 degrees C, and we have the COX production peak around 580 degrees C. And indeed, this is confirmed also by the fact that the NO conversion profile remains constant and equal to the Fent value for the whole run. This clearly indicates that NO is not able to interact with soot, and even in the presence of NO, the oxidation of soot is carried out by oxygen alone. A very different situation is evident when we add NO2 in the feed stream, both for the case of NO2 only, 500 ppm, or for equivalent amount of NO2 and NO, 250 ppm each. We can see that the soot combustion is shifted at very low temperature, both for both the cases, indicating a promoting effect played by NO2 on soot combustion. And if we look at the profiles of the NOx, we clearly can see also that the production of CO2 and CO is associated with the consumption of NO2 and with the simultaneous release of NO. And indeed, we can explain this behavior considering that in this case we may have these two reactions reported in red here, which are related to the combustion of soot by NO2 that produce COX with release of NO. We can also see that in the case of the experiments run with high amounts of NO2 in the feed stream, once we have completed the soot combustion, we have a release of NO2, which however is decomposed to NO and oxygen due to thermodynamic reason. And when we have less amount of NO2 fed into the system, we can see that we still have the COX peaks present at 580 degrees C, indicating that at high temperature oxygen may contribute and compete with NO2 for soot combustion. So we further move to the analysis of what happens when we have simultaneously ammonia and NOx present in the feed stream. Again, as before, we analyze the 4 different reacting mixture, and for the case of oxygen only or NO only, here we are comparing the results just shown that were obtained in the absence of ammonia, which are the solid line, with the results obtained in the presence of ammonia in the feed stream, which are the dotted lines. We clearly can see that ammonia doesn't seem to provide new routes for soot oxidation. Indeed, the results are really similar one to another, but for a slight anticipation in the COX peaks evident in the presence of ammonia. So, in the presence of ammonia, the combustion of soot is still carried out by oxygen. But again, when we add NO2, the situation is quite different, both for the cases of NO2 only or equimolar amount of NO2 and NO in the feed stream. If we look at this experiment here, we can see that the promoting effect that was evident in the case of absence of ammonia is no more evident when we have ammonia in the feed stream. Indeed, the soot combustion is going back to higher temperature, and we have the COX peaks centered around 580 degrees C. So, this is evident also for the case of the NO less present in the feed stream. So we can clearly say that in this case, the presence of ammonia may inhibit the enhancement played by NO2 on soot oxidation. This may be explained considering that the presence of ammonia enables the occurrence of these two reactions here, the NO2-SCR reaction and the fast-SCR reaction. So in this case, these two reactions obstruct NO2 and prevent him from reacting with soot. Anyway, the two experiments here clearly point out that the DeNOx reaction at low temperature are the preferred pathway for the soot, for NO2 usage. So we have the consumption, the relative consumption of NO2 in both soot combustion and the DeNOx reaction, but the DeNOx reaction may consume more NO2 at low temperature. We finally look at the effect of soot on the SCR reactions. And we started looking at the ammonia absorption process. Here we have the TPD profiles obtained in the presence and in the absence of PM in the nitroreactor that were obtained after having absorbed and dissolved ammonia at 150 degrees C. We clearly can see that the presence of soot enlarged the TPD profile, and this is maybe explained considering that on soot we may have acidic side that can be formed by interaction of soot and water at high temperature. And the shift at high temperature of this profile also indicate that the new sides are kind of strong for ammonia absorption. We then move to the analysis of the ammonia oxidation reaction. Here we have the results obtained in the presence of soot. We have ammonia oxidation starting at 350 degrees C with production of nitrogen only. And in this graph here, we compare the ammonia conversion measure in the presence of soot with that measure in the absence of soot. We see that the presence of soot enhances the ammonia conversion and shift it at lower temperature. And looking at the literature, this may be explained considering that on soot we may have formation of oxygenated compounds that may act as oxygen donors and thus enhance the ammonia conversion. We move down to look at the standard SCR. Again, here we have the results obtained in the presence of soot in the microreactor, and here we compare the DeNOx performances in the presence and in the absence of particulate matter. We can see that both at low and high temperature, the presence of soot inhibits the standard SCR reaction. And actually, considering that we found that NO was not able to interact with soot in the presence of oxygen, we may say that this, at low temperature, this inhibited effect may be related to covering effect played by soot on the copper active sites of the catalyst. While at high temperature, the lowering of the performances may be explained, reminding that we observe an increase in enhancement in the ammonia oxidation reaction that can lower the DeNOx performances in the high temperature region. Very similar results were obtained in the case of the fast SCR reaction. Again, we have a loss of activity both at low and high temperature. And again, as done before, for the low temperature region, we can invoke covering effect played by soot, but also the competitive consumption of NO2, which indeed was able to interact with soot at low temperature. And in this way, we are consuming NO2, which is no more available for the fast SCR reaction. And at the same time, the NO2 consumption with the NO2 reaction with soot may produce NO, and thus we are shifting the 1-to-1 ratio to a lower value. And this is evident also here, where we can see that in the run performed in the presence of soot, the consumption between NO and NO2 is no more 1-to-1, as typical of the fast SCR activity. The high temperature region behavior again can be ascribed to the enhancement of the ammonia oxidation reaction. As opposite to the case just seen, for the case of the NO2 SCR reaction, we do have an increase in the activity at low temperature. And also, this is associated with a lower amount of N2O production. So we can increase definitely the performances of the NO2 SCR reaction if soot is present in the microreactor. This may be explained again, considering that in this case we have the competition for the NO2 usage between the NO2 SCR reaction and the soot combustion. So NO2 is used to burn soot with releases of NO. And this means that the flat value of NO2 to NOx that was equal to 1 is actually shifting to lower values which are closer to 0.5, which is the value associated with a very active fast SCR reaction. And in this way, we are increasing the activity of the system. So to wrap up what we have seen up to now, what we've done was to study systematically the mutual effect of DNOx performances and soot combustion reaction on a copper-zeolite catalyst. We have seen that NO has no effect on soot combustion, whereas NO2 does play a role. A significant enhancement of soot combustion was observed with increasing amount of NO2 in the feed stream. We also observed that the presence of ammonia does alter the reactivity of soot combustion because we have a competition for the NO2 user between the SCR and the soot combustion reaction. And we have seen that at least at low temperature, we have the ammonia SCR reaction are a preferred reaction pathway. And this clearly means that ammonia reduces the SDPF acid regeneration capability. We also investigated the effect of soot on the DNOx performances. We have seen that the presence of soot may provide new signs for ammonia absorption, which are actually strong signs. We have seen that the standard and the fast SCR reaction may be slightly but negatively affected by the presence of soot, and as opposite, the NO2 SCR reaction may benefit from the presence of soot, as the soot NO2 competition may move the unfavorable NO2 to NOx peak ratio typical of the NO2 SCR reaction to a value which is much more effective. So we further move to analyze other types of soot, actually looking at two real soot that were collected at the laboratory of applied thermodynamics using in passenger car vehicles or at MTU labs in Friedrichshafen using a large non-road vehicle. And we did use the same approach as before. So for both the real soot, we have investigated the effect of NOx on soot oxidation, the effect of the simultaneous presence of ammonia and NOx on soot oxidation, and the effect of soot on the DNOx activity. First of all, we wanted to understand if these different soot were really different. And as we were not allowed to characterize them from the morphological or chemical point of view, we just ran a TG experiment, both in air or in nitrogen. We can clearly see that by comparing what we obtain in the case of the lab soot and MTU soot, that the MTU soot seems to be less reactive. Indeed, we need to get to higher temperature in order to get its combustion. So let's start to look at the lab soot, so the more reactive soot, and we look again at the 4 different reactive nature. Here we have only oxygen as soot oxidizer or oxygen in the presence of 500 ppm of NO. As was the case of Printex Q, we do not have very different results in both cases, indicating that NO also in the lab soot is not able to interact with it. Then, again, a different situation is evident when we add NO2 in the feed stream. Again, we got a shift to a lower temperature in the soot combustion. We can clearly see that by CO2 and CO production, which is occurring starting from 150 degrees C, with the simultaneous consumption of NO2 and release of NO. If we compare the results that we have obtained on the last suit with those obtained over the MTU suit using the MTU suit, we clearly can confirm that both in the presence of oxygen alone or by co-feeding NO2 and NO in a similar amount, the last suit seems to be more reactive. Indeed, we have both in both cases the oxidation start at lower temperature with respect to the less reactive MTU suit. We then move to the analysis of the simultaneous presence of ammonia and NOx on the feed stream. So as done before, for the last suit, here we compare what we obtain in the presence and in the absence of ammonia. And again, as was the case of the Printex used suit, we do not have big differences, but for a slight anticipation in the ammonia in the COX profiles obtained in the presence of ammonia. Again, the situation changes when we add NO2 in the feed stream. So the positive effect played by NO2 to the soot combustion is cancelled, and the soot combustion is going back to higher temperature, played mainly by oxygen in this case. And this is due, as was the case of Printex due to the competition that we have here between the reaction of the ammonia SCR reaction that consumes NO2 and the soot combustion that consumes NO2 as well. Again, we can look at the same aspect over the MTU suit. Here we have, for instance, the experiments run in the absence and in the presence of ammonia for the NO2 to NOx ratio of 0.5. And again, we can see that the presence of ammonia inhibits the soot oxidation. And if we compare directly the LAT and the MTU suit, also in this case, also under SCR condition, we do find that the LAT suit is more reactive than the MTU suit, and so may change the soot oxidation temperature. Finally, we'll look at the last suit on the effect of soot on the ammonia SCR reaction. Here we have the two runs that were obtained by running ammonia absorption-desorption at constant temperature and then by running the TPD. And as was the case of the Printex use, by comparing specifically the TPD curve, the TPD profile, we can see that the presence of soot increases the ammonia absorption capacity and also provide new, stronger sites for its absorption. Looking at the overview about the SCR activity, here we have the comparison for ammonia oxidation, the standard SCR, the fast and the NO2 SCR of the performances obtained in the presence and in the absence of soot. As was the case before, we got an enhancement of the ammonia conversion. In ammonia oxidation, we probably for the presence of oxygenated compounds on the soot. The standard and the constant SCR seems to be slightly but negatively affected by the presence of soot, while we got a big enhancement in the performances associated to the NO2 SCR, both in terms of DNOx performances and selectivity to nitrogen. And indeed, this is ascribed again to the competition between for the NO2 user that we have with soot combustion that may alter the NO2 to NOx ratio and shift it to values which are closer to that of the fast SCR. So again, we wrap up what we have seen. Well, in all cases, I would say that we have very similar effects using MTU, LAT, or Printex use soot, even if we have evidence that we have difference for the two suits. The main point here are the enhancement of low G in soot combustion that may be obtained by feeding NO2 in the feed stream. We have the competition between the SCR reaction and the EM combustion for NO2 user, which actually is won by an ammonia SCR, at least the low temperature. And we also have a big enhancement in the NO2 SCR reactivity, and this is due to the fact that soot combustion by NO2 may alter the actual NO2 to NOx ratio. We have also seen that we have differences among the different suits, and we have ascribed possibly these differences to the different composition of the different suits. Specifically, we have found that the carbon balance related to the MTU suit were always higher than those associated with the use of the last suit. And this may be due to the greater amount of non-carbon species present on the last suit. So we wanted also to understand if the catalyst has a role in this chemistry. And to do that, we ran new experiments using the Cu-zeolite catalyst and in the presence of MTU suit. As before, we used the same approach. So here we studied the effect of NOx on soot oxidation on the iron zeolite catalyst for the different oxidizing mixtures. We have here pure oxidation by oxygen, and here the oxidation is carried out in the presence of NO also. And again, as before, we don't have a strong effect, so NO is not able to interact also in the presence of iron catalyst, but a different situation is obtained when we add NO2 into phase, both alone or in equimolar amount with NO. Again, we have a lowering of the temperature associated with soot combustion played by NO2. And if we look into more details to the effect of the catalyst, here we can compare for three different experiments the soot combustion obtained by pure oxygen, oxygen NO, or by NO2. And we clearly can see that at least for oxidation played by oxygen, in both these cases, as we know that here is oxygen alone doing the combustion, we can say that the copper seems to be a little more reactive than iron in enhancing the soot combustion. And to analyze this aspect into more detail, we wanted to investigate the effect of the catalyst. And for this, we ran experiments studying the soot combustion over the iron zeolite, over the copper zeolite, but also in the presence of only cordierite or bare substrate, which is a zeolite system. We clearly can see that the CO2 production is very similar in all the cases, but for a slight enhancement obtained in the case of copper. So this clearly tells us that there is no catalytic effect played by the catalyst in soot combustion, but for a slight enhancement played by the copper. So actually, iron zeolite seems not to catalyze soot oxidation. We further go on with the work by analyzing the effect of the simultaneous presence of ammonia and NOx on soot combustion. Here again, we can see for the four different reactant mixtures the comparison for the experiments run in the presence and in the absence of ammonia. And as were the previous case, we do not have strong differences when the oxidation is carried out by oxygen, both for oxygen alone, for oxygen and NO, while ammonia affects negatively soot combustion when NO2 is present in the feedstream. Again, this is due to the competition for the NO2 usage between the soot oxidation chemistry and the SCR chemistry. Finally, we analyzed the effect of soot on the ammonia SCR activity, starting from ammonia absorption-desorption process. Here we can compare under iron zeolite the two curves obtained during the TPD following the absorption-desorption process at 150 degrees C, obtained in the presence and in the absence of soot. And of course, as was the previous case, we get an enlargement of the TPD profile because the soot present in the microreactor provide additional sites for ammonia absorption. Looking again at the overview for the ammonia oxidation, the standard SCR, the fast SCR, or the NO2 SCR, we see that we have similar results for ammonia oxidation, which is enhanced by the presence of soot, for the standard and the fast SCR, which are negatively affected by the presence of soot, but we have different results for the NO2 SCR. What we have seen up till now is that we were able to enhance the NO2 SCR by changing the electron ratio. In this case, up to 300 degrees C over the iron zeolite and using the MTU soot, the two curves are overlapped. And we may consider that, in this case, we have two different phenomena that can explain this. The first one is that we are using the MTU soot, which was found to be less reactive than the other soot, as we said before, over the copper catalyst. Less reactive means that we have to wait up to higher temperature in order to have a competition for the NO3 usage in this case. And at the same time, here we have the iron zeolite catalyst, which is very well known to be more active in the NO2-SCR reaction rather than the copper zeolite catalyst. So again, what we are saying is that up to 300 degrees C, the only reaction going on here is with the real NO2-SCR reaction. So the presence of soot does not alter the situation. So to wrap up the effect of iron, we found that actually we do not have any catalytic role played by iron on soot combustion. Otherwise, we found that we do have effect, of course, related to the presence of soot. We have a low enhancement of soot oxidation with NO2 feed. We have seen that ammonia may kill this possible low T enhancement by competing through the SCR reactions, of course. We have seen that ammonia affects soot oxidation and indeed may move to higher temperature, the COX peak, And we have seen that all the main reactions that are typical of the SCR catalyst are negatively affected by the piano presence. And we also seen that the copper-zeolite catalyst seems to perform a little bit better than the iron-zeolite catalyst in soot oxidation. So as a final part of my talk, I would like to spend a couple of words talking about the work that was performed through a collaboration that we did with NTU and with the Laboratory of Applied Thermodynamics in Thessaloniki, in which we have used the findings of this first part of the work, of this fundamental work, to develop a model of the real SDPF system. So what we've done was to first derive the intrinsic kinetics of the SCR catalyst, and we did that for a copper-zeolite catalyst, and then this kinetics has been implemented in the AxiSuite model of the SDPF component. And in this model, further, the kinetics of the soot oxidation and also of the DPF functionality of the SDPF component have been calibrated independently. So the main thing here is that on the basis of the results that I will show you, we have the indication that the chemistry are independent one from another. And this means that in the model we have calibrated independently the kinetics associated with the different functionalities. So once we have developed this model, the model was validated against data collected using the passenger car engine and also the big non-road vehicle. And this work has been recently published in Emission Control Science and Technology. So first of all, I would like to show you the derivation of the intrinsic kinetic for the SCR catalyst. To do that, we used a model which was published recently by our group, which is a 1D isothermal antivariate blood flow model of the microreactor. And we also took the kinetic scheme and the rate equation from this paper, which, however, described the behavior of an iron-zeolite catalyst. And so we proceeded in simplifying the model in order to take into account the differences typical for a copper-zeolite catalyst. And more specifically, we have neglected the overconsumption of ammonia in the standard SCR. We have neglected the inhibition of ammonia, which occurs at low temperature in the standard SCR. And we also neglected the reactivity of N2O with both NO and ammonia, which occurs at high temperature. So to calibrate the model, we ran a number of experiments in the absence of soot, of course, on the copper-zeolite catalyst, analyzing according to a hierarchical order the different reacting systems related to the SCR process. Here we can see the experiments run to analyze the ammonia absorption process. We have experiments at different temperature and varying also the amount of ammonia fed into the system in order to derive a model which is able, of course, to predict these variations. We can see that the dots, which are the experimental results, are quite in line with the model fit, which are the solid line. So we proceeded to the following reacting systems. We looked then at the ammonia oxidation, to the NO oxidation, and to NO2 decomposition. Again, we vary some of the experimental conditions, just like the space velocity or the oxygen amount. And as you can see here, again, for the comparison between experiments and model fit, we were pretty satisfied with the description that the model was able to provide in terms of all the concentration profiles associated with reactants and products. And finally, we want to describe the full reactivity system related to ammonia, NO, and NO2 and oxygen. And this was done, of course, by varying the NO2 to NOx fit ratio, 0, which is the case of the standard SCR, or 0.5, which is the case of the fast SCR, 1, NO2 SCR, and we also tested intermediate value to validate the model. And again, in this case as well, we have a good reproduction with adequacy of the model to fit the experimental results. So once we have provided the intrinsic kinetic of the SCR, we have implemented this into the AxiSuite commercial software platform that for the description of the real SDPF component. And in that, we have proceeded to calibrate independently both the soot oxidation kinetics and the DPF functionalities. To do that, at Laboratory of Applied Thermodynamics, they have used an engine test bench in which they run a number of experiments using a Daimler engine for passenger cars, followed by a DOC or a Catalysis DPF, and finally by the SDPF component, in which we used, of course, the same catalyst that was used for the calibration of the SCR kinetics. Here we can see some of the results that were obtained from these test results. As the first part of the work, the diesel particulate filter calibration was done. First of all, the permeability for the clean filter was fitted, and here we can see the results in terms of pressure drop for different exhaust flow at different temperature. Then, with this good result, they further proceeded in calibrating the filtration efficiency by loading the amount of soot with time, and again we get a good reproduction of the experimental results. And indeed, by simply simulating the pressure drop, they have a good adequacy of the model in order to predict the pressure drop of the loaded SDPF components. So again, once calibrated the part related to DPF filtration, they proceeded in calibrating the soot oxidation chemistry. And they did that by using new results that were obtained at different temperature, of course, in the absence of ammonia. Again, we can compare here the model fit with the experimental results, and we have a good agreement between the two. So in order to validate the experiments also in the presence of ammonia and to look at what happens when we have the system working for both the function, new experiments have been run at different temperatures by co-feeding ammonia. And we got very good agreement between the results and the simulation that the model was able to provide. But what I would like to stress more is that if we compare the results that we have obtained in terms of burn soot for experiments run in the absence or in the presence of ammonia, we clearly can see that the presence of ammonia decreases the amount of soot that can be burned. And this is in line with what we have observed experimentally on the model scale in microreactor. And indeed, we can use also the model to decouple the contribution related of soot combustion for the different oxidizing species. And we can see for the orange and the blue part of these parts here, which are related to soot combustion made by NO2, that again, if we move from the experiments run in the absence to the run in the presence of ammonia, we are decreasing the contribution of these two reactions, while we keep almost the same the other reactions. So again, we have a very good confirmation of what we have observed on a small scale. And also, I would like to stress that the SDPF model that was built by considering independently the kinetics of all the functionality of the SDPF is indeed able to reproduce these results. The model is now built, and we can use that to play with it. And I would like just to show you these results here that shows the NO2 concentration profiles in soot and wall layer during a passive regeneration obtained at 450 degrees C at the inlet channel. We can see the amount of NO2, which is present in an experiment run with and without ammonia. The blue indicate very low concentration, while the yellow and the green here indicate higher amounts of NO2. So again, in the absence of ammonia, we can allow the system to have more NO2 in the system, more NO2 present in the catalyst wall, and thus allow a better consumption of the soot present in the filter. Finally, the model has been also used to simulate the results obtained on a bigger scale using the Nuremberg engine, but due to the fact that in that case the SDPF component was realized with a different substrate, they had first to adapt the permeability of the system. Once adapted that, we can see here in terms of ammonia, NO2 or NOx conversion that the model was able to reproduce in a very good way the results obtained in terms of SCR performances. So, as a final part of this talk, I would like to summarize by saying that we have derived the intrinsic kinetics of the SCR over a powder SCR catalyst, and we have implemented these kinetics into a physico-chemical model of the real SDPF component. On the real scale, we also confirmed the negative effect of ammonia-SCR reaction on the soot oxidation rate. And the model was indeed able to reproduce these results by simply superimposing the different chemistries. We have first validated the model against real data collected with 2 different scales and collected using data for runs using different engines. And I would like also to say that this model can be now used to develop new and improved system or to develop improved strategy for the ammonia solid threat. And with this, I would like to acknowledge the team financing the work and realizing the experiments on the North vehicle, and Professor Constantis at the Laboratory of Thermodynamics for the SDPF implementation in the AxiSuite and run on the engine test banks using passenger cars. I would like also to acknowledge the group in Milan, the Laboratory of Catalysis and Catalytic Processes, and of course I would like to thank you all for your kind attention.
This talk is open for questions.